Surprise! Yes, we're back, but not quite in the classroom. So I thought I'd be in the classroom. We'd go over some things, and I'll talk about this more in class, but here's one of the first videos that we'll have. We're starting with Chapter 8, which is all about different integral methods that you can use when you get hard integral problems. And we're only going to cover a few that we need to, so we're going to do a little more than half the chapter. But I want to start off with just a quick review of how we could do the integrals we've already learned. I figured that might be good after a couple weeks off. By the way, if you need a list of all the integral rules, page 522 is once again a nice place to see that entire list, although you could always just look at pages, note cards. So make sure you take a look at that, and then let's look at our first few examples. This video is just going to be a handful of examples of methods you've used before. So you got these three examples up on the board, and you know, we've done stuff like this before, but the first instinct might be to try use substitution. And I hope you can see why in each of these examples, use substitution isn't going to work. It all comes down to the derivative. So we see the derivative of 4x, and we look at that. We see the derivative of 2x, and we look at that. We see the derivative of 2x, and we look at this. We know that these are not going to work by just the normal means. Notice that in this situation, when we substitute in, you're still going to wind up with u's and an x. We really don't want to see this situation where we have u's and x's still here. No, the x squared and the 2x can't divide out, and that 5 is really just messing it up. Same thing over here. The x's can't divide out because you need to divide an x out of the 2. In all three of these situations, u substitution is not working. So here's some quick methods that hopefully you remember. For example 1, we're going to rewrite this problem. We're going to expand it. Foiling that binomial gives us a nice, easy power rule. Super simple. Number 2, if the numerator is a higher degree or an equal degree, you can rewrite the problem by dividing. When you divide, and in this case we have to use long division, your quotient, the answer to the division problem, will be put back in here. And now we have a very easy power rule and one of our special rules that we learned in late chapter 5. And then finally for number 3, it doesn't quite work. It looks like use substitution has a chance, but we're going to split it up. So now we have two distinct integrals and we can actually solve both of them. The first by use substitution, the second by one of our special rules. So these are now all solvable because we rewrote them. So that's really important. If you can rewrite an integral to make it easier, do it. And here's the answers, by the way. One thing I'd like to point out is that on here, you can write arctan or inverse tan. These are almost the exact same thing. And I did rationalize that front number. It was supposed to be 1 over a, which was 1 over the square root of 3. So I rationalized the number. If there's a variable, I didn't worry about it. And then likewise over here, I would have to use u substitution with u being x squared plus 3. It's a natural log problem. And once again, we have the tangent. I wrote it as inverse tangent that time. There's 3 different review methods. Let's see if we can come up with a couple more. These next 2 are going to involve some trig identities. So let's see if any of those identities can pop up. Let's go with the most famous ones, or the ones I keep telling you might have to know this year, which is the Pythagorean identities. These little babies harken back straight to the Pythagorean theorem. It's just we're using trig values to represent the x values, the y values, and the hypotenuse, the radius. And if you want to get the next ones, divide everything here by sine squared to get the next identity, or take this original and divide everything by sine squared. But here's what we can do. Take a look at the first one. That looks like I wrote it wrong. Yeah, let's try that one again. Yeah, that original version was way too easy. That was just a straightforward idea. This is cotangent squared, which we have no rule for. We know the integral of cotangent. We know the integral of cosecant squared. We don't know how to do cotangent squared. Use substitution won't work. So use an identity. With that identity now plugged in, we can integrate very easily. And there we have an answer. The other one you might not have ever seen before, but it's still going to use the Pythagorean identities. It's quite a mess because we have trig and then other numbers, but we can simplify that trying to get to our Pythagorean identities. Watch the rest on the next video.